In this video, we're going to talk about low-pass filters and high-pass filters. A low-pass filter passes low-frequency signals, but it impedes high-frequency signals by greatly reducing its amplitude. So in the upper left, we have a low-frequency signal. And as you can see, the amplitude has been, for the most part, relatively the same. It hasn't been reduced. Here we have a high-frequency signal. And notice how much the amplitude is reduced. And so a low pass filter, it passes low frequency signals almost unimpeded. But the high frequency signals, the amplitude is greatly reduced. Now the first type of low pass filter we're going to talk about is the RC low pass filter. And the circuit looks like this. So here we have the input voltage and the output voltage. Now this circuit looks similar to a voltage divider circuit. Let's call the first resistor R1, and let's call this R2. Now, if you recall, the output voltage of a voltage divider circuit is going to be R2 over R1 plus R2 times the input voltage. And what you need to understand is this. As R2 increases in value, the output voltage will increase if you keep R1 the same, since R2 is in the numerator. So thus R2 and the output voltage, they will be proportional to each other. If you decrease R2, the output voltage will decrease. Now for the circuit on the left side, the output voltage is going to be the capacitive reactance divided by the impedance times the input voltage. The impedance is equal to the square root of R squared plus XL minus XC squared. Now because we don't have an inductor in this circuit, XL is 0. But what you need to understand is this. The capacitive reactance is kind of like resistance for capacitor to AC signals. The capacitive reactance is 1 over 2 pi FC. So as the frequency increases, the capacitive reactance decreases, since F is on the bottom here. And as XC decreases, the output voltage decreases as well. Because XC is on the top, these two are directly related. So what you need to understand is that high frequency signals, they will pass through the capacitor. Low frequency signals are blocked by the capacitor. They're impeded by it. They can still pass through it, but with much more impedance. So the low frequency signals will go towards the output, whereas the high frequency signals will be sent to the ground. And that's how the low pass filter works. It passes low frequency signals to the output while attenuating high frequency signals. So for the RC low pass filter, this circuit has a frequency response that looks like this. Here we have F on the x-axis and the decibels on the y-axis, and this is the shape of the graph. So this would be the cutoff frequency, FC. At the cutoff frequency, the signal drops by 3 decibels from its maximum. Now to calculate the cutoff frequency, you could use this formula. It's 1 over 2 pi RC. So as you increase the capacitance, the cutoff frequency decreases. And as you increase the resistance, the cutoff frequency will also decrease. Now, at the cutoff frequency, the output voltage will be 70.7% of the input voltage. And at this point, you'll have a decibel drop of 3 dB. And you can calculate that using this formula. The decibels is equal to 20 log times the ratio of the output voltage to the input voltage. So if you were to type in 20 log 0.707, you would get negative 3.01 dB, which corresponds to a 3 decibel drop. So that's where that number comes from. Now there's something that I want to mention regarding capacitors and inductors. So as we've seen earlier in this video, the capacitive reactance is 1 over 2 pi Fc. So as we increase the frequency, the capacitive reactance decreases because F is on the bottom. These two are inversely related. And if we decrease the frequency, the capacitive reactance increases. So the impedance is high when the frequency is low. That means that capacitors, they block low frequency signals. They greatly impede low frequency signals. And the impedance is low when the frequency is high, which means that capacitors allow high frequency signals to pass through relatively unimpeded. For inductors, the inductive reactance is 2 pi FL. Notice that F is on the top of the fraction this time. So as we increase the frequency, the inductive reactance increases. These two are directly related. And as we decrease the frequency, the inductive reactance decreases. So the inductive reactance is high when the frequency is high, which means that the inductor blocks high frequency signals. It impedes it. High frequency signals could still pass through, but it's greatly impeded. Now, the inductive reactance is low when the frequency is low, which means that the inductor allows low frequency signals to pass through relatively unimpeded. So keep this in mind. High frequency signals can pass through capacitors. Low frequency signals can easily pass through an inductor. A capacitor blocks low frequency signals, and an inductor blocks high frequency signals. Now, there's another type of low pass filter that we need to talk about. And this is known as the RL low pass filter. It has an inductor and a resistor. This time the output voltage is directly across the resistor. Now the output voltage will be equal to the resistor divided by the impedance C, which is the square root of R squared plus XL minus XC squared. And this is going to be times the input voltage. So now, notice what happens if we increase the frequency. At high frequencies, the inductive reactance is going to go up. These two are directly related, as we mentioned before. But now XL is not on top of this fraction. It's only on the bottom. So as we increase XL, the output voltage will decrease. Now, if we decrease the frequency, the inductive reactance will decrease, and the output voltage will increase. So notice that the output voltage is high when the frequency is low. This means that we have a low pass filter. Anytime the output voltage is high when the frequency is low, you have a low pass filter. For high pass filters, the output voltage will be high when the frequency is high. But we don't have that situation here. Now, the inductor will allow low frequencies to pass through. As you mentioned earlier, low frequencies can easily pass through relatively unimpeded by an inductor. The high frequencies are greatly impeded by the inductor. So this is another reason why this circuit is a low-pass filter. Now the frequency response looks like this. It's very similar to the frequency response for the RC low-pass filter, where we have a cutoff frequency FC, and the signal drop will be 3 decibels. Now, for this circuit, the cutoff frequency is R over 2 pi L. So as R increases, the cutoff frequency will increase. And as L increases, the cutoff frequency will decrease. So the resistance of the circuit is directly proportional to the cutoff frequency, but the inductance of the circuit is inversely related to the cutoff frequency. So that's it for the RL low-pass filter. Now let's talk about high-pass filters. High-pass filters allow high-frequency signals to pass through the circuit while blocking low-frequency signals. So let's start with the RC high-pass filter circuit. So in this circuit, the position of the capacitor and the resistor have been switched from the RC low-pass filter, as you can see here. The output voltage is directly across the resistor. The output voltage is going to be equal to R divided by the impedance Z, which is the square root of R squared plus XL minus XC squared. And then this will be times the input. Now keep in mind, the capacitive reactance is 1 over 2 pi FC. So as the frequency increases, the capacitive reactance will decrease, because anytime you increase the denominator of a fraction, the value of the whole fraction goes down. Now, as XC decreases, what do you think is going to happen to the output voltage? Keep in mind, XC is in the denominator of that fraction. So if you decrease the value of the denominator, the fraction will increase in value. The output voltage will go up. Likewise, if you decrease the frequency, the capacitive reactance will increase, the output voltage will decrease. So notice that the output voltage is high when the frequency is high. So that is a characteristic of a high-pass filter. Now keep in mind that the output voltage can't increase forever. There's a limit. When the frequency is very, very, very high, let's say if the frequency goes to infinity, at most, the output voltage will approach the input voltage. This is not an amplifier circuit, so the output voltage can't be more than the input voltage. So the output voltage will increase until it reaches the input voltage. Now the frequency response for this circuit looks like this. It's different than the other RC low-pass filter. So this would be the cutoff frequency, and this right here would be the maximum value of the signal, and we have a drop of 3 decibels at the cutoff frequency. Now the cutoff frequency, this formula is going to be the same. It's 1 over 2 pi RC. And the gain in decibels is going to be 20 log V out over Vn. So the output voltage will be 70% or 70.7% of the input voltage at the cutoff frequency. So we have some similar formulas, but the shape of this graph is different. as the frequency increases, that is, as we go to the right, we can see that the output voltage is going to increase. The graph is going up. It's not going down. In the case of a low-pass filter, we saw the signal, the output signal, decreasing when the frequency increased. As you travel to the right, you can see that the graph is going down. So that's a characteristic of a low-pass filter. But for a high-pass filter, the signal increases with increasing frequency. So for a low-pass filter, you can see that the output signal is high when the frequency is low. And for the high-pass filter, you can see that the output is high when the frequency is high. Now let's talk about the RL high-pass filter. And let's compare that to the RC high-pass filter. So in the RC high-pass filter, we know that the capacitor allows high-frequency signals to pass through, but it blocks low-frequency signals. So we can see why that's a high-pass filter. Now for the RL high-pass filter, both high-frequency and low-frequency signals can flow through the resistor with the same resistance. Now the inductor allows low frequency signals to pass through it. So I'm going to write FL for low frequency signals. However, the inductor, it blocks high frequency signals, which I'm going to write FH for. So the high frequency signals have no choice but to go to the output. So we can see why this is a high pass filter. It allows the high frequencies to pass through to the output while attenuating the low frequencies. And the same is true for that circuit. Now the RL circuit, the RL high pass filter that is, has a graph that is very similar to the RC high pass filter. So this is the cutoff frequency. And the formula for the cutoff frequency is R over 2 pi L. So it's very similar to the RL low pass filter. The formula is the same to calculate the cutoff frequency. So that's it for this video. Now you have a basic review of low pass and high pass RL and RC filters. Thanks again for watching.